We know that the sample mean x bar, it's our single best guess without additional information of this unobserved population mean mu. But we might ask, how far off is our guess? How far off do we expect our point estimate to be? Well, the standard deviation of the sampling distribution, we call this the standard error of the sample mean. The standard error of the sample mean, sometimes called just SE for short, it equals the population standard deviation. So the standard deviation in the population for the variable of interest, it's that population standard deviation divided by the square root of the sample size. So it's sigma divided by the square root of lowercase n. A few things to note about this standard error of the sample mean. First of all, nature just gives us the population standard deviation. We don't have control over that. That's just a property of the particular variable we're looking at. So in this case, when we're looking at education in Iowa in the early 20th century, that standard deviation in the population for educational attainment in years, we don't have control over that. So in the population, if the population standard deviation is smaller, if that standard error is going to be smaller. So we would expect that our point estimates to have less variability from sample to sample. However, we do have control over the sample size n. So just note that when we have a larger sample size, when that denominator is larger, because that numerator is fixed, when that denominator is larger, then we're going to have a smaller standard error of the sample mean, meaning that that standard deviation of the sampling distribution is going to be smaller. Right? So the key point here is that in general, right, we're going to have less sampling variability. Our sample means are going to vary less from sample to sample, the larger the sample size in which we use to calculate those sample means. So let's look at this in just a little bit. So since we conducted a census, we in fact know the population mean for educational attainment, but we also know the population standard deviation sigma. We can just calculate basic summary, numerical summaries on our set of data. So these are the set of values for our data on educational attainment in Iowa using the full census data. We see that in the population, the standard deviation is about 3.98 years. So that gives you the spread of educational attainment. And the average, of course, is in the population is 6.98. In practice, we wouldn't observe these values, but it's useful for understanding the properties of the sampling distribution. So in this case, since we're collecting a sample mean based on a size of 10 people, the standard error for any one of our sample means is going to be that population standard deviation divided by the square root of our sample size. So we take 3.98, that's the population standard deviation for educational attainment, and we divide by the square root of our sample size 10, we get this value of 1.26. That is the standard deviation of our sampling distribution. It is equivalently the standard error of the sample mean. It gives us an idea of how far off, in general, we expect our sample means to be from sample to sample. Right? The smaller the standard error of the sample mean, we expect less sampling variability. Right? The larger the standard error of the sample mean, then we expect our samples to bounce around a lot more. So let's look at the sampling distribution of sample means using 100,000 samples. So this is a dot plot. The dots are so small they look like bars, but it's 100,000 sample means. And for each sample mean, it's based on a size of 10. So it's just a bunch of sample means gathered with replacement. And in this case, this distribution of sample means, it's centered very close to the population mean mu, which is 6.98. And then if you're to take the standard deviation of this distribution of sample means, you would find that that standard deviation is very, very close to 1.26. So it's just the same. That standard deviation of this distribution is in fact sigma divided by the square root of n. And you can see that the smaller the standard error for the sample mean, the tighter this distribution will be around the population mean mu, meaning we would expect our sample means to vary less in terms of the distribution around that population mean. The larger the standard error of the sample mean, the more sampling variability we will have for any given set of point estimates for that population mean. And we can see this. So suppose instead of basing our sample means on size of 10, what would happen if we had based a sample mean based on a size of 100? So we have one distribution here in which the standard error of the sample mean is 1.26. So this is just the population standard deviation divided by the square root of our sample size, which is 10. And then we have another sampling distribution in which we have the population standard deviation divided by the square root of a larger sample size, in this case, a sample size of 100. So when we have a bunch of sample means based on a size of 100 rather than 10, you can see the distribution in both cases, they are centered on the population mean. Both of these sampling distributions are centered on the population mean mu of roughly 6.98. But the distribution in which that's based on a larger sample size, that spread is smaller. The standard error of the sample mean is smaller. And so we would expect the sample means to bounce around much less for the distribution of sample means based on a larger sample size than a smaller sample size. And this can be useful because in general we don't want too much sampling variability. If you take a simple random sample, we still know that that sample mean is going to be our single best guess without additional information for the population mean, but we're going to be a little bit less confident about that particular point estimate if we know the sampling distribution is going to have a wide spread. If that sampling distribution is very tightly bound, it's very narrowly bound around that population mean mu, we're going to be more confident that any particular point estimate is going to be pretty close to the population mean. So to recap what we know about the sampling distribution so far, whenever we take a random sample, we can calculate a particular sample mean. Right? We've done this many times. You just take all the values and you divide by the sample size, and that's x bar. This is a point estimate for the population mean. Keep in mind that each random sample is going to produce a possibly different sample mean. That is sampling variability. To put it another way, if we repeatedly draw samples of a size of lowercase n from any population, the values calculated in each sample will vary. But if we repeat this process of taking random samples and calculating sample means, and we create a dot plot, then we have a distribution of sample means, or what we call a sampling distribution. Right? And the key point here is that the mean of the sampling distribution, it's centered on the population mean mu. And we can know how far off we are from the truth, from this population mean mu, by examining the variance of the sampling distribution, which is sigma squared divided by n, or the standard deviation of the sampling distribution, which is sigma divided by the square root of n. When that standard deviation of the sampling distribution, we call the standard error of the mean. We call it an error because it's sort of an idea of how far off we expect a point estimate x bar to be from our target, from this unobserved population mean mu. The other thing to keep in mind is that if you noticed the sampling distribution, it's roughly symmetric, right? And it's mound-shaped, meaning the left and right sides of the sampling distribution look more or less the same, and it's mound-shaped and it's centered right on that population mean mu. So you might say, how can we summarize these results? Well, we can summarize these results in terms of the central limit theorem. This is probably the most important aspect about inferential statistics. It's crucial that you really understand this. The central limit theorem states that if random samples of size lowercase n are drawn repeatedly from any population with a mean mu and variance of sigma squared, then when n is relatively large, so roughly larger than 30 or equal to 30 for most distributions, the distributions of these sample means will be approximately normal. And we use this notation here. So in this case, we say the sample mean, x bar, is distributed as, that's what that tilde means, is distributed as a normal distribution centered on the population mean mu with a variance of sigma squared divided by lowercase n. And if we take the square root of that variance, the square root of sigma squared divided by n, we get sigma divided by the square root of n. And that we call that the standard error of the mean. It's simply the standard deviation of the sampling distribution. The key point here is that the central limit theorem says not only that this distribution of sample means, the sampling distribution, is centered on the population mean mu and has a particular variance or standard deviation. But this distribution is symmetric and mound-shaped. To put another way, it's a normal distribution. Right? This is very cool, right? We can take any population no matter its distribution. So here we have 4 completely different populations. In the population, educational attainment might be normal, right? It might be roughly symmetric, or might be kind of skewed. There might be some outliers, or it might be uniform. Maybe everybody has the same educational level, or maybe it's really irregular. It's a very odd sort of distribution. Regardless of what the distribution of educational attainment is in the population, by repeatedly and randomly drawing sample averages from any population, we can create a new distribution of sample means that we know will be normal. Right? This is crucial. The distribution of sample means is itself normally distributed. So this is a summary of the sampling distribution. At the top here, we have 4 different distributions in the population. And then what you can see is that the distributions below show various sampling distributions. So you can see that, first of all, for each of these sampling distributions, they're roughly symmetric and mound-shaped. Right? When the sample size is pretty small, there's greater spread, there's some skewness. But you can see as we get closer and closer to, say, 30 in terms of the sample size, that the distributions are all pretty normal. Right? The sampling distributions are roughly normal, they're mound-shaped, and for each of these distributions you can see that they're roughly centered, but especially as we get larger samples, centered on that population mean mu. And for each of these, the actual standard deviation, the standard error of the sample mean, is in fact, it's the same. It's roughly the idea behind it is really a function of the sample size. So as we increase that sample size, you can see for each of these sampling distributions, this spread gets smaller. So this is why we often want, if you look at pollsters or many survey companies, they try to get a sample size of roughly 500 to 1,000. That's because that standard error of the sample mean, it's going to be pretty small. It's going to be pretty tightly bound around that population mean mu. The central limit theorem, right? It's very powerful because it tells us we can make inferences about the world around us from relatively small random samples of target populations. We don't have to conduct a census. We can just collect a random sample. Right? And since we know the properties of the sampling distribution, we can use the sampling distribution to make inferences about a population based on a set of representative data gathered from a random sample. So, for example, typically we want to know about entire population, all Europeans, all birds, and so forth. But, it's expensive to do that. So we can just use a particular sample to make generalizations or inferences about the population. Now, the question you might say is, how large of a sample do we really need to say something about a population? Well, for most distributions in the population, because you can see some distributions of the population could be kind of irregular, maybe the population is normal, but in general, right, for most distributions, as long as we have a sample size of roughly greater than or equal to 30, we will have a sampling distribution that is really quite close to normal. It's mound-shaped, symmetric. If the distribution of the population is really quite symmetric, then you can get away with a smaller sample size, say around 15. And in fact, if the actual distribution of the population is normally distributed, for example, if you divide height by gender, among men, the distribution in a population for height is usually normal. Right? It's a normal distribution. Among women, it's approximately normal distribution as well. So if you just look at height within genders, the distribution of the population is pretty close to normal. In those instances in which the actual distribution of the population is approximately normal, then the sampling distribution of the mean is going to be normally distributed as well. So the key idea here is that before we're looking at dot plots, right, of the sampling distribution, in fact, we can actually just model the sampling distribution using the normal distribution model. Right? The sampling distribution is centered on the unobserved population mean mu, and it has a standard deviation given by sigma divided by the square root of n. To put it another way, the standard deviation is the population standard deviation divided by the square root of our sample size. We only need these two values to model the sampling distribution because we know the distribution is normal as long as the sample size is larger than about 30 or so, or the distribution of the population is normal, or if it's symmetric, we can get away with a slightly smaller sample size. The key point is that we can model the sampling distribution using the normal model. And so here we have the normal model of the sampling distribution. You can see that this model, it's centered very near the population mean mu, and the standard deviation is approximately sigma divided by the square root of n. So this is just a model of the sampling distribution for the sample mean. We can use the normal model. We don't actually have to have a population and select random samples as we did before. Now, the key point is that we can also convert all these sample means. We can convert them to z-scores. Right? So previously, we've been looking at the sampling distribution in terms of the sample means. But we can convert these sample means to distances, sort of a standardized set of distances from this population mean mu. So supposing we know the population mean mu, we can take each sample mean, subtract out the population mean mu to see how far each sample mean is either above or below the population mean, and then we can divide by the standard deviation of the sampling distribution, or the standard error. And in this case, we can use a standard normal version of the sampling distribution. Now we've converted the distribution, so the population mean is now 0, and the standard error is now equal to 1. So we can, in fact, use a standard normal model for the sampling distribution as long as we convert our values of the sample means into z-scores, right, by subtracting out the population mean and dividing by the standard error. So this is the standard normal model of the sampling distribution. You can see the population mean is now rescaled, so it's 0. Recentered rather, so it's 0, and then the standard error is rescaled, so it's now equal to 1. And these are all values of z-scores for our sample means. Several things to know for our discussion so far of the sampling distribution. A point estimate, it's simply our best guess from our particular sample of some population parameter. So the sample mean is without additional information, it's a single best guess for the population mean mu. The sampling distribution of the sample means, it's going to be centered on the population mean mu, and it has a standard deviation given by sigma divided by the square root of n, which we call the standard error of the sample mean. The shape of the sampling distribution is going to be very close to normal for most distributions if the sample size is, say, 30 or greater. And with that, we will stop now and talk about, explore some of the aspects of the sampling distribution. Then we're going to dive deeper into the sampling distribution for our second part of this lecture.